Okay, whatever. Yeah, okay.
All right. You want to just? All right. Yeah. So, so Faré here pretty much helped start the Haskell, the Boston Haskell meetup stuff here. You were here like the first few.
Maybe. Yeah.
And then you lost interest.
Well, yeah, I was too much in my list stuff.
And went back to playing with parentheses. And ran away to New York. But apparently, still has excuses to come up to Boston every once in a while. So I was able to convince him to come up and give a talk. So I have absolutely no idea what it is he's going to talk about today. So I'm going to simply give him the floor and let him talk.
Hi, so I am Faré Rideau, and I'm going to tell you today about first-class implementation, turtling down runtime meta levels and PC-loosering up. So this is work I mostly did like 20 years ago when I was working on the Tunes project, which is the greatest, or some of the greatest vaporware that was never written. And I'll give you a glimpse of it. And this is where I put this PDF for the current presentation. So this talk is salvaged from my aborted 1999 PhD thesis, the title of which was The Semantics of Reflective Systems. And basically this is the hand-wavy part that is not completely hand-wavy that I'm going to tell you about. And at the time, Patrick Couzeau, I don't know if you've heard of Patrick Couzeau? No? Abstract interpretation guy, the guy who made abstract interpretation big, which is type analysis, static type analysis done the right way. So he was teaching abstract interpretation at École Normale Supérieure, but all I was interested in was going the opposite direction, not abstract interpretation, but concrete implementation. And my take-home points for today are that implementation is the same thing as abstract interpretation, but going the other way, and that save points are a key concept. You already know that concept, but it deserves to have a name of its own or whatever. My second main point is that first class is the opposite of magic. When something is not first class, it's done magically for you by the system. When something is first class, it's open and accessible to the user. And you need first class save points. Then I'll talk to you about applications of these ideas from what I call migration in general, including process migration, optimistic evaluation, I think we'll skip that, etc. And how you can compose first-class implementations for fun and profit. And my last part will be how to factor your code in a different way based on this notion of first-class implementations. So my plan of my talk will be that. And let's start with formalizing the notion of implementation. So you may have done some semantics about lots of things, and this is to simplify what abstract interpretation is. You start from C, or C will be a computing system in which you write software, your programming language, something, and you are trying to find something A, an abstract meaning A to things in C. For example, a type, static type. If you've used the Haskell, for instance, you may have heard of this programming language Haskell, in which programs have types. So you will try to extract a type from your program, and it has to preserve structure. It has to be functorial. It has to, if there's a transition in the base system, the concrete system, there should be a corresponding transition in the abstract system. So if something changes type in the concrete system, it will change type up there. And if it doesn't change type in the concrete system, it will not change type in the abstract system. So it's just an arrow that preserves the type. And why is it arrow dashed instead of straight? Because in general, these things are partial functions. It is not every program has a type. And so actually it's a functor from a subset of your programs to this abstract thing. And what is concrete implementation? Concrete implementation is the opposite. It goes the other way. So it's the same diagram, but now where's my mouse? So aliens ate my mouse here. The thing that you program in is the abstract system A. So A will be Haskell now. And you want to find something concrete, for instance, x86 desktop, in which you will implement that. And you will add a lot of extra information. You will add something like memory addresses for where this variable is bound or where this const cell is stored. So we'll add information. So there are two main distinctions between concrete implementation and abstract interpretation. In abstract interpretation, you have usually a static program and you want to analyze it statically. And so you will consider all the possible executions of the program and you'll try to extract a type or an analysis from that program. When you implement the program, of course, you don't care about all the possible executions. You care about the executions that you're given. I want to execute this and not something else. So I will instead encapsulate the dynamic runtime properties of my program instead of just the static compile time properties. And that's why I will do that with operational semantics instead of denotational semantics. When you study type systems, you tend to do it with denotational semantics. When you're doing implementations, you'll tend to do it with operational semantics. So because our arrows go down, it's a downward thing, and not abstract. So the functorial, the direction that preserves the arrows is functorial up. When you go down, you don't preserve the arrows. You can introduce more structure. You can introduce more structure, and so. When you go up, it's essentially lossy in terms of information. When you go down, it's noisy. You add information, you add labels, you add things. And when you go up, it's deterministic because there's only one type possible for your program. When you go down, it's non-deterministic because there are plenty of label address assignations you can give to your data object. Yes, two questions. This one first.
Yes. So can you distinguish this approach that you're developing from the idea of specification and refinement? So it seems like
it's very similar. It's the same general. Yes, it's the same general thing that refinement and specification. Yes, it's the same general idea. Yes, and
I just wanted to make sure. You
okay.
understood.
Yes. So it is the same thing, indeed. But here are categories. So I'll have diagrams with objects X and Y that are in a category C with a morphism phi between them. And for an operational semantics, it will be a state that will transition to another state inside a category or subcategory and with some kind of annotation that represents the side effects that happens when you transition from something to something else. And when I have a bar here, it means as usual that this is a function phi associates y to x. And I have more arrows. This one is just it's injective, and this one is it's partial. Okay, so here is a partial function. When I write this, if you only know the total functions, that means this. This means that you have your concrete category here, C. You have O, which is a subset of C. So J is an injection. So O is a subset of C. It's a full subcategory. So it has all the arrows between 2 points in O that are also points in C. Exists also in O, but it's what you expect to be for a subcategory. It's a subset of this. And then you have a function phi from O to A. And so I can write that this way, where if I have this, I have that. That's the introduction schema for my, the diagram for introducing the partial function. Or I can write this way. I don't know if you can see it. What I did is I put the conclusion in blue and the premises in black. So when you see something with some black and some blue, it means if we have all the stuff in black, then with this rule we can deduce the stuff in blue. So this means here, if I have an abstract category A and a concrete category C and a subset O of C with a injection J and a morphism phi, a functor phi from O to A, then I have this partial functor big phi from C to A.
Does abstract or concrete mean anything at this point?
Here, at this point, just no. Just means that the A is up and the C is down from this arrow. So, and this is more or less the same diagram, but with the states or with the states of my categories. If my categories are operational semantics, that means that I will have C, which is an element of the category concrete category C, O, which is the same element viewed as it's O equals C. It's viewed as a member of a subcategory O, and to O I associate A, and this is the same as associating directly A to C through this partial function. Okay. Now, operational semantics, I already said that you'll have states like X, Y, and Z. So for instance, a trivial program, you want to implement print hello world, and you will want to implement, say, hello world as with a stack thing. So you start from the beginning of your program, you push hello world string into your stack, and then you print it. And so here you could say that S will be my operational semantics, and here SE, I will write E because I say, hey, this is in a subset of S, which I'm interested in because it has some side effects and not other side effects. And I will say, oh, hey, here's F, the side effects that's there. And in the end, I can exit the program because I've done what the program does. Okay, so soundness. Soundness is a property that if you don't actually have an implementation, or you have a very buggy implementation. It is a property that if I'm starting computation, so I start from an abstract computation A. I implement it somewhere, somehow, as C. I start doing some computations in this concrete category C, and it gives some answer C prime that happens to have a meaning A prime. Remember, not all states in the concrete implementation, in the concrete category, have a meaning in the abstract category. It's a partial function, but this one happens to have an answer. So I have an answer. It could be an intermediate answer or the final answer. And if I'm given an answer, the answer better makes sense in the abstract category. So if you don't have this diagram, your implementation is buggy, throw it away or fix it or fire or sue the person who gave you this implementation because it's not really an implementation. Okay.
So usually an abstract interpretation of this idea of the Galois connection between the abstract and the concrete domains, is that basically what this is describing?
I think this is much more simpler than the Galois connection, but I think it is just, it may be related to that, but this is like, I think this is simpler than that. I think a Galois connection has something more than that. But
this is basically that both paths are equivalent.
yes.
Going
Yes.
to the abstract. And not the
Yes.
concrete.
Well, so the idea of a Galois connection is the correspondence between the abstract and the concrete.
Yeah, it might be the same. I forgot all my quizzle.
You described this as sort of an operational thing.
Yes.
But it's Galois connection is sort of static thing.
Possibly. I think Galois connection, for Galois connection, you need to know the other sense and you need a cofunctor or something. So
You have to be more careful about splitting up syntax and semantics. And
Yes.
Then you have the adjunction between the two.
yes. So I think I'm more primitive. This is more primitive than the Galois connection, I believe. Totality, that's a property that you don't always have. Obviously, if your abstract system is infinite and your concrete system is finite, you will not have totality. You will not have, for every abstract state, I can implement it with a concrete state. But most of the time, you deal with things that are reasonably, that fit in your memory or whatever, or you deal with an abstraction of your computation that is infinite. And most of the time, you want to have totality for your implementation. So for every abstract state A, I want to be able to find a concrete state C that corresponds to A. That's a pretty reasonable thing that you may want to have for your implementation. Something else you may want
Is
to
phi
have.
implied there? Should phi be blue there?
No, phi is the constant implementation that you're considering. Phi is total if this holds.
Got it.
I'm sorry, I forgot what the different arrows.
Blue,
So this is
okay.
a partial function.
This is an association. This is with a bar here. It means it's the usual. C has an image A. To C, I associate A with the function phi.
And I assume you're ignoring resource constraints.
I'm ignoring what?
You're ignoring finite resource constraints.
Yes. Yes. Usually, to have totality, you have to ignore things, or you have to have both things finite, or whatever. But I'm just saying that soundness is something that everyone must have. If you don't have soundness, you throw away this implementation. If you don't have totality, it can. You only have to be total enough. You only have to to implement the states that you care about. You don't have to implement your entire algebra.
So you can have states that don't correspond
Yes.
to an abstract. So.
Yes, you can have abstract states that don't have a concrete state, like numbers that are too big to fit in memory, things like that. Completeness. So completeness says if I'm starting from computations that I started to implement A, and I know how to go from A to A prime in the abstract system, then I want to be able to do the same thing in the concrete system. It's also a property that you don't want every implementation to have, but when you have it, what it means is that you can basically debug or single-step your debugger. It means that I can start in some state and, hey, I want to do this. So this is basically single-stepping or multiple-stepping in your debugger. Another property that you may or not may want or may not want to have is what they call advanced preservation or weak liveness. Weak liveness means if I'm not stuck in the abstract system, I want to not be stuck in the concrete system. So if the abstract system can advance, so I suppose that I have a subset A plus of A that typically won't have self arrows, identity arrows. I have a subset A plus of A, and if I'm not stuck in the abstract system, I want to not be stuck in the concrete system. That's also a reasonable thing to have.
And that's implied by completeness.
No, you can have wait. Oh yes. Completeness is when not only you have that, but A prime can be the same as A second. Yes. This is implied by completeness. This is weaker than completeness. Indeed. This is liveness. What I call liveness is if I have a long enough chain of advancing concrete computations, they will eventually go past some abstract computation. So I'm not churning in vain. I cannot do infinite number of concrete steps without making some advance in the abstract steps. And if you could even add a bound to in less than n concrete steps, I can do one abstract step. Or you can have lots of variants. And this is strong liveness where I want to actually synchronize to one of those advanced states while I'm advancing. And obviously, it's something that you may not want to have for parallel implementation, but for sequential implementation of a sequential program, that might make sense to have something where naturally you find a safe point all the time. And you would say, oh, can I have A prime being the same as A second here or in the previous one? And yes, you can, but once again, then you better have A and be a confluent system, otherwise you can't have that. If A is confluent, then yes, you can always go past the progress. If A is not confluent, if A is non-deterministic, then it can branch one way and branch another way, and then you can't have A prime, you can't force A prime to be the same as A second.
So does your strong liveness property basically prohibit certain optimizations that would otherwise be permitted under?
Yes. Strong liveness prohibits a lot of optimization. Since with strong liveness, you must reach each and every intermediate step of your abstract computation. So yes, so there are properties. Some properties you don't want to have in your implementation, but sometimes you want to have it, or sometimes it's good to know that you have it to make some other reasoning. Okay, so composability. Composability is the fact that when you have an implementation phi and an implementation psi, and an intermediate system M between A and C, you can compose them, and hopefully all of the previous properties will be preserved. Actually, not all of them are. I think weak liveness is composable, but strong liveness, completeness, totality are composable. That is, if I have totality for phi and psi, I will have composability for psi. If I have totality for both the intermediate ones, I have totality for the total thing. And a lot of interesting properties do compose and some don't compose. So you have to be careful how you write your properties so that they do compose. Okay. And this is an interesting diagram because here I'm introducing an intermediate system between A and C, which allows me to compose my implementations. And then instead of having one intermediate, I can have n intermediate things, and I can have a compiler in many, many passes where every pass does some transformation, but I just need to prove every pass correct to prove that the whole thing is correct, for whatever correctness is with soundness plus extra properties that I may want to have. But the interesting problem is not just that, it's also that. And what I changed here is that your concrete implementation C is the same, A, your programming language is the same, but what you really care about is P, your program. Your program is an operational semantics, and you are describing it with A, and A is itself implemented in C, so your programming language Haskell is implemented on x86, and your program is implemented in Haskell, and you want your program to have all the interesting properties. You don't care of properties of Haskell if you don't have this property in your program P. And the properties that I'm thinking of here is, well, there's the same diagram, composibility, with lots of total functions. It's a bit uglier. But it's a bit uglier, but we see here that all these objects are basically subsets of the same. So an element of C is equal to the element of this and equal to the element of that. And here you're transcoding it to a different space A, and here it's B. So
this is the composition by fullback, right? So the composition
yes,
spans.
yes. Well, okay. But the property I was thinking of that you don't get is what I call observability or PC losering. So who here has read the article about PC losering by Alan Bowden? Good. Shoeless burst.
You might want to expand PCLSR.
Okay, PCLSR. Okay, so back in the 70s at MIT, there was an operating system called ITS, the Incompatible Time Sharing System, that ran on PDP-6 and PDP-10s, and that was incompatible with CTSS, a compatible time sharing system developed by IBM and MIT. And all the hackers use a PDP-6 and PDP-10 with ITS, and developed it in Lisp, etc., and lots of assembly. ITS had this thing called PC losering. You could look at the state of another task. It was a multitasking operating system, just like CTSS. And you could look at another task, and when you looked at another task, you were guaranteed to only look at it outside of kernel mode. When you look at another task, it's never in the middle of a system call. When you look at another task, you know what the state is perfectly encoded. The other task is stable, in a stable state. A stable state with respect to the invariant that you're not in the middle of the system call doing something weird, and if you change something, then it will have totally burnt your program. So they say you cannot catch a program with its pants down. But with its pants down, with respect to one particular invariant, the system invariant that says, you can encode, you can faithfully encode the state of the program from what you get from the image, from the memory image of the other task. And PC losering, more generally, it means exactly that. When interrupting a program, so I have a computation that I'm starting, I'm interrupting it, and in general, C prime does not have a meaning. And it's a partial function, so the intermediate state in which you catch a program when you interrupt it has no meaning. For instance, the typical example, I'm trying to atomically move some value from one register to the other. I'm taking $100 there, and I'm putting $100 here. And you better not interrupt me in the middle, or you're going to break the invariance of my program. Or whatever data structure. Your data structure has invariance in the middle. I'm doing non-atomic memory operations. You better not catch me where at the time that my data structure is wrong, or the whole program will crash if you try to do anything interesting. Other than restarting. If you stop just to restart, just to close the program, that works. But that's the only interesting thing you can do with a thread if you don't have observability. Observability says that if I interrupt it, then I can somehow roll back or roll forward to an interesting state, C seconds that has a meaning. The C0 here means that I want this transition to happen in a subset of C that doesn't have input. If it has output, it can be output that are guaranteed to succeed, and hopefully it will succeed in a few microseconds or something. So it's a small subset of C. I want to be able to synchronize from C prime to C second with minimal amount of work and work that is guaranteed to succeed. And every programming language implementation has that. If it has a concurrent garbage collector or a parallel garbage collector, because your program will mutate the heap, and at some point you want to garbage collect it, so you have to stop the other thread and say, hey thread, I'm going to stop you and I'm going to garbage collect. So if you're in the middle of a transaction, if you're writing something and the state of the heap is wrong, I won't be able to garbage collect. So please, please, make sure your heap is in order, make sure all the invariants of your heap are preserved, and then it will be able to garbage collect. So this is a very important property that, so every Java implementation or Haskell implementation has this under the hood. I can start the state, please synchronize your state such that I can garbage collect. The problem is that in Java you don't have that. When I interrupt my thread, it's in a state that has a meaning with respect to the Java programming language and the JVM and its invariants. But it does not have a meaning with respect to your program. Your program may be holding a lock. Your program may be in the middle of this memory transaction. Your program may be doing anything. And all you can do is just Java servicing, because all you have is this Java invariant. So you can do your garbage collection, but you can do anything interesting with respect to your higher level program, because you don't have observability with respect to your higher level program. So what you need is a way to let your higher level program specify what is or isn't a safe point. And people are slowly coming to that with transactional memory or things like that, but there's still not a general purpose way to declare safe points in your programming language. Yes?
What does the acronym stand for?
PC loser, and I think PC was a program counter, and loser was a nickname of users in ITS. All users were loser, LSR. So it's just getting the program counter of the loser of another task, of the loser.
Yes, program counter losering.
Putting it into user mode.
No, it's grabbing the program counter of another loser. You have another task.
Forcing it from kernel mode to loser mode.
Yes, you want to have its yes, you want to have its in user mode. Does that make sense? Okay, so I want to have observability at the level of my programs and not just at the level of the programming language that I'm using. Okay, so now what do I do with these things? Here are some categories for you. So I'm implementing here cat class in Haskell, or something that looks vaguely like Haskell, where a category S is something that has an associated arrow type, and every arrow has a domain, which is the point it comes from, and a codomain, which is the point it goes to, and I can somehow compose arrows. So I don't have dependent types, so I can't encode in the type system the fact that the domain, the codomain arrow of the first one must be the domain arrow of the second one, etc. You can guess what happened. And when I apply an arrow, I take this arrow and I take a point that better be the domain of the arrow, and then I can produce another point that will be the codomain while doing some magic effects, maybe. So in Haskell, you would have actually a monad here. The dotted arrow will be two monads of some monad of this. Okay, so the operational semantics is just a category where I have a function run and a function done. Done tells me, hey, is my state done? Can I reply now and say I'm done, or do I have still to keep running? And run here is also monadic, whatever it has side effects. It's typically non-deterministic. You can't predict how many steps. It's not running one step, it's running n steps. So it's a non-deterministic function here. So I'm breaking it with also a dashed arrow. So this is operational semantics, and from then you can have, for instance, eval, which would keep running until it's done. Or I could have a function advance that is guaranteed to run, but to only return after having done some work. So I could add lots and lots of functions, and I could actually add functions that correspond to the properties I have. What is the computational content, for instance, of totality? No. The first implementation. So that's just the operational semantics. An implementation is an implementation of A with C is a functor from C to A with additional operations that correspond to. This is just a functor from C to A. And for totality, I have a function implement that goes from A to C. But it's also a non-deterministic function, and it's a partial function if I don't have totality, it's a total function if I have totality, but in general it's also non-deterministic. There are many ways possible to implement a given abstract state in the concrete state. Completeness corresponds to a function step that would take a C and the associated A implicitly, and an arrow here that corresponds, that starts from the associated state A in the abstract state, and that would return the arrow in the concrete state. And here again it's non-deterministic, that's why I put it dashed. What is the computational content of liveness, or weak liveness, or other liveness? It's a function advanced interpretation that takes a concrete state and advances to another concrete state in a way that it goes past an abstract state. So it's not just advanced C+, it's advanced in A+. So it's a moral equivalent of advancing in A+, but implemented in C. Does that make sense? Okay. So what's the computational contents of observability? It's the safe point function that would take an intermediate state C prime and would find you the state C prime prime. Prime, would you say that? Second?
Double prime?
Double prime. Okay. Compilation. Compilation, the simplest way to think of compilation is I have an abstract language A, and I'm implementing it with a concrete language A. And so it's just a usual function implement for my implementation. That's the simplest way of thinking of compilation. Here, a slightly more interesting way of thinking of compilation. Here I have a source language S, and I'm interested only in some properties of my program. For instance, I write my lambda calculus with labels X, Y, Z, but I'm not interested in X, Y, Z. I'm alpha converting them or away. So A will be an abstraction of S. And moreover, I will have equations in my abstract language that correspond to the fact that I don't care if function is reduced or not, or whatever, these functions are equal to me. So I will have lots of equations in A that I don't have in S. In S is just plain text or whatever it is that you use as source code. So, and then, once I have done all these equations, I will try then to find an implementation of that. And this is, I think, a slightly more interesting view of compilation, where compilation is about having a source code and abstracting it away, and then reconcretizing that. And then you find that, unhappily, A in the general case is non-computable. Like whether two functions are equal is not a computable thing. So I can't really, if I tell you that I'm doing that, I'm lying to you. What I'm really doing is this. What I'm really doing, what the compiler does, I'm taking my source code S, and yes, it has some meaning A, abstract meaning A that I'm interested about, but this meaning is not computable. So what my compiler really does, it goes to a subset or superset, depending on how you see it. It goes at something U that is an understandable part of the semantics. The part of the semantics that the computer does understand. And it has fewer equations than in A. So there are fewer things that the computer can say are equal. But it can say they are equal, and then it will implement that. And the diagram commutes. So you have what I call a semantic gap between what the computer understands and what is the ideal thing you really care about, assuming it exists, or the platonic ideal of what you care about. And then a compiler specifying a a compilation is specifying now three things. It's specifying the operational semantics of things you care about, with all the rewrites that you're allowed to do, all the optimizations that the compiler is allowed to do, because this optimization does not modify what I care about the program. And then you will interpret your program in terms of this understood semantics, and then recompile it to something more concrete. And then I have, static type systems. So what are static type systems? You have your source language that also has an abstract semantics, and from that you can extract the type. And now that you extract the type, because you have subject reduction that says that in terms of operational semantics, there are no exomorphisms. There is no way that you have an arrow from something of type T to something of a type T prime, where T prime is different from T. All the arrows are, in T, all the operational semantics arrows are endomorphisms. Your program can never go wrong. So now that you know the type 2 of your program, you can say, hey, actually, in the subset S and S2 of S, and which corresponds to a subset A2 of A, and then I can understand that. And because I know tau, I can do a lot of optimizations and whatever, and transformations that I could not know if I didn't have this. So this is static type systems. And now for applications of first-class implementations. Okay, so my favorite diagram is migration. Actually, maybe my second favorite. My favorite was observability, and this is basically observability followed by re-implementing the same thing differently. So migrating a process from migrating a process from one implementation to another is, hey, I'm starting a computation with one implementation, and I'm deciding, I'm going to stop that. Hey, I don't like this implementation, it's too slow, or it's on my phone, and now I want to move to my laptop, and then to my desktop, and then to the cloud, and then to the Google, whatever, some brain, Matryoshka brain, something. I want to move my program without stopping it. So this is without stopping it. I'm starting my program on my cell phone, and then I'm moving it somewhere else by just changing the implementation. And once you have this notion of first-class implementation, this is trivial. I'm just applying observability and recompiling in a different context. So if I have first-class implementations, and my implementations do have observability, I can trivially do things that most people say, oh, this is something great hack, but like great low-level hack that no one can pull except me. No, anyone can do that at any level they want if they have observability. And when you hammer migration, everything is, process migration is migration. Garbage collection is migration. You have your abstract system, which is just an abstract graph where you don't care about where in memory the objects are, and you are labeling it in concrete with addresses for your nodes of your graph. And so a garbage collection is just finding a different association from nodes to memory address. So garbage collection is migration. Zero copyrighting is just that you're going to reinterpret this buffer as this object rather than that object. Instead of copying the buffer, you just reinterpret it. You're changing the interpretation. Dynamic configuration. If I have my computer displaying this window on this screen and I want to display it on that screen, I can just say, hey, I'm recompiling my program now. I will be pixels there instead of here, and with 24-bit colors instead of 8-bit colors or whatever, I can recompile my program to be optimized for just the display I have. So I can dynamically recompile things. And git compilation is, this function is right now implemented as running this interpreter or this representation, and now it's instead the same function being implemented as a compiled something. So everything, when you have migration, everything is migration. And of course you can say, oh, I don't actually have to extract a representation of my abstract thing and recompile it. I can instead try to compute a migration function M that will do the transformation without going through the pain of extracting an entire representation.
What is that?
What is what? This crudely means this is a non-deterministic thing. I could, in this case, it should have been a straight line. Good call. This should be just a straight line. but it just means that M is a non-deterministic function. So, okay, and we'll say, oh, what does it mean to have a different implementation underneath? We'll say, underneath it's still the hardware. Well, yes, okay, you want to have this. The hardware doesn't change. The hardware will just represent implement things as the state, the pair of the state and the implementation that goes with it. And then, okay, now I don't have this change from C to K. I can just implement things with H all the time. And then you can factor out the intermediate state, and you have directly, I'm going to stay in the same implementation, and I'm just going to change the thing, the interpretation. I'm keeping both the state and its interpretation. Okay, migration tower. Oh, I love that. This is stepping back from the previous diagrams. I have my program that is in some semantics view. So what is up is not inside the computer. The computer only cares about what is under you. Under you, okay, whatever. And typically U is implemented with some virtual machine V, and there will be some migration from some towers or some turtles or something under V. And in the end, it all goes on the hardware, and this these things will remain the same, but I can change arbitrarily things between V and H. Between V and H, it's or between actually U and H, it's fair game. The system can at any point change anything because it's guaranteed to never change the semantics that you care about, which you specified at some point as being these are the things I care about, the rest, what is under this I don't care about. Oh, and here semantic tower, because what you care about might change. At some point I have my source code S, and I start to run it, and I say, hey, this is some understanding of what this source code does, and that's what I care about. But sometimes you can say, no, actually what I care about is something more abstract. So do these optimizations or do whatever, I really only care about that. Or I only care about this thing that's even more abstract, more optimizations are allowed. And sometimes you say, oh, there's a bug in my program. I want to debug that program, so I will go all the way down there. And please tell me, like, each single step with stupid, low-level operational semantics, but tell me at which point some value in some variable did what was there. Or you can go even lower, or even look at the address, because actually it's a bug in your kernel when you swap whatever. Processes. I once had to debug a bug at level 8 where the Linux kernel didn't say some MMX register or something. So sometimes you want to stay very high level, and sometimes you have to go all the way down. And for the same program, while it's running, you should be able to change, to zoom in and out. For the same program, hey, I really don't care on which machine it's running. Run it at whichever, the best you can. Or, oh, I want to debug it on it has to be actually on my laptop. And it has to be, don't change the thing while I'm debugging it underneath, and etc. So you want to move in the semantic tower while the program is running. Actually, maybe you don't want. I want to do it. Okay, optimistic evaluation is a complex thing. Just say that sometimes you can, it's another way that you can have, this is not a composition of, this means that you can have some computation C here that assumes that something is right, and it can be invalidated in one path, or it can be confirmed in another path, and then if you can commit your transaction, you go there, and if you have a failure in the middle, you go there. And you can draw lots of diagrams for many things. This diagram does not matter much in particular, but what I mean is there are other ways to think about building implementation from other implementations than just composing them. So you have things like, aspect-oriented programming. Aspect-oriented programming is when you have a concrete system and you have 2, 3, or more different abstract interpretations of what should be done, and you want to reconcile them. So I will give you A1, A2, and A3, and you're asking the system, hey, please find C that satisfies all these aspects of my program. And you can think of it as constraint logic metaprogramming. So you have a metaprogram the logic metaprogram that tries to find C knowing the constraint A1, A2, and A3. So yes, with this formalism, you can find lots of familiar things have a simple expression in this formalism. What are natural transformations of implementations? Saying any kind of automatic instrumentation, like code and data coverage, is you are going to insert extra instruction or extra accounting for what's happening. Omniscient debugging. Who here knows omniscient debugging? Or you're going to have a treat. Google omniscient debugging, and it's a wonderful thing where basically it runs your entire program and it records every choice and every binding and every modification done in your program, and then at the end of your program you have, crash because Fandango on core something is null. Why is it null? Well, you can go in the past.
Usually time traveling debugging would be the
time travel debugging, yes.
Figure out the Haskell.
Okay, time travel debugging, yes, exactly. So you can do just an automated instrumentation of your implementation to get time travel debugging. Or resource accounting or parallelization can be seen as a natural transformation of implementation. Or orthogonal persistence virtualization. Plenty of things can be seen as transforming automatically an implementation into another one with a means different than just composing it with something underneath. Okay, so my last part is about runtime metaprogramming architecture. What I call a runtime architecture is something where you have a development platform, so it can be Emacs or whatever inferior IDE you're using instead. It can be any kind of user interface shell, whether it's a Unix shell or whether it's your Windows something. You have some kind of interface between what you want to do and what the computer does for you, or an operating system, or an application management system for your distributed or virtualized application. That's a runtime architecture. And I argue that if you are building anything like a runtime architecture, then you will find a great use in first-class implementations. And what I propose is that you should assign to every program a semantic tower. So semantic tower has a semantics on top. So you specify some U, which is a known, understood semantics of your program, and everything on top is a semantics that is implicit of your program, and everything underneath is a turtles that infinite amount of turtles that you have between you and the hardware. And when you want to modify something about how your program is changed, you actually move the turtle up above the level U. Hey, I really care how this is done, so I'm going to raise the semantic tower and look at n turtles below me. I may change them, swap them for other turtles that I care about, and then when I stop caring, I can give it back to the system to care about. So the semantic tower is all the things under your program, the turtles under. And I argue that you will want to add this notion of semantic tower, explicit semantic tower, to your programming languages you build, the kind of DSL you build, and you will want to demand from your compiler writers to provide you with handles and first-class implementations for your programs, because that is mighty useful. And then, when you have that, you will be able to control this tower either statically or dynamically. And statically, it's just that you specify, hey, I want to compile this program with this meta program, etc. And dynamic control, you want to have it at runtime too. And to have it at runtime, you need to have a controller. So every tower will have a meta program that says, hey, now let's shift these things, let's do something to my tower. And you can do it at runtime. And then many towers may or may not have the same controller, or there can be some sharing there or not. That's a different question, but you will want every tower to have some meta program that controls what's going on. And in effect, this is user accessible virtualization. In most operating systems now, you have some notion of virtualization where the operating system can virtualize processes, but it can only virtualize them at one particular abstraction level, which is the abstraction level of Unix processes with which are virtual x86 processors with lots and lots of system calls. So it's a very, very complex fixed operational semantics that you are virtualizing. What I'm arguing is that instead of virtualizing this very low-level fixed architecture, you should be able to virtualize any operational semantics that you care about. At the level of abstraction you care about, not higher, not lower. You should be able to do that. And then should they be able to control side effects that happens in your implementation and control how the I/O is connected to your program while it's running. So of course, you will have reflective towers. I don't know if you ever read any of these papers from the 80s about reflective towers. This is generally the same idea as this, except that they didn't use as much semantics and proofs and formal systems. They were more hackish back in the days. But this is the same idea where every controller itself has a semantic tower and can be itself controlled. And so you have also turtles, but it's always all the way down, but it's a different dimension. So I would have to add a third dimension to my diagram to represent this kind of semantic things. Okay, so what does implicit I/O? I like implicit I/O. Implicit I/O is when your program just says, hey, I want some input. I want, for instance, I want some characters, or I want a file, or I want an integer, I want something. Just give it to me. Here's a tag so that if you want to distinguish between many different integers that I may request from you, I'll give you a tag. So, and give me some input, or here's a tag and here's some data, and just output it. And then the abstract system, the program, will just say, I need some input, or I hear some output. I don't care what you do with it. And what will do the input or the output will be the controller, will be the the meta program that handles the controller at runtime. So you can have virtualization of effects at language level, and you can dynamically reconfigure, because the same program, when it's running, can say, I want something. And right now it's running on my cell phone, so it will pop some menu on my cell phone. And after I migrate the program to my desktop or my laptop, it will pop the menu on my laptop. Or at some point I will say, hey, I am tired of taping things. Just pipe the data from this input file and let it work from there.
Sorry, is this that the input-output format is sort of auto-magically created?
Yes.
Or is this that there's some presumably massive universal namespace and I just give you a tag? It's
your controller can handle this. I mean, obviously there is a lot of, if you want to do structured things, you will have to build some structure in your meta program, in your controller. But from the point of view of the program, it's simple, it's magic, the input will magically appear. And that's important, which means that you now have decoupled completely the computation from the input mechanism.
So are you saying it's both? That there is this global massive namespace of tags? And
yes.
Because that has some quite non-trivial implementation details.
Yeah, but
I'm so comfortable.
It's a global. It's maybe the namespace is global, but the dynamic space of is not global. Every process has its own private controller, so the controller does not have to share the data with someone else.
Okay.
It's just a name that is, maybe the name is global, but the actual data is not. Yes.
It's more like the language feature version of doing everything in a free mode.
I'm just trying to make sure we don't like.
Yes. Yes.
Okay. I'm just trying to make sure we don't like just. Oh yeah, there's a magic layer that implements log-free consensus or something like that.
Yeah, that's the aspect-oriented thing that was earlier.
Okay, so you can do things like that, and then have dynamic configuration. So you have decoupled the input-output from the computation, and that can help with performance, because now when configuration changes, you can migrate your code to be optimized for the specific configuration it is in. So once again, if I'm bleeding things directly to the sound card, I don't need to have n buffer copies, because I will directly compile my sample directly to my sound card in the correct format with a minimal amount of encoding, and and zero copy. And they can also skip unobserved computation, something that Haskellers must appreciate. When a computation is not needed, it will not actually be computed. If I'm displaying a video online and I only care about the music because actually it's a music video, but I just using the music in the background, you should not even have to compute the frames, the video frame. You could just drop them and just look at the length of the video frame and skip to the rest without doing any of the display decoding and encoding, decoding work. So I know this joke. There was this book by Greg Egan, Permutation City, in which a guy uploads his brain to a computer, and since he's misanthropic, is that what you call it? Misanthropic, he decides that he hates the world, he hates other people. So after having uploaded his brain to a computer and he created his own private war with everyone he cares about, all the simulated people he cares about, he disconnects his he fully disconnects his I/O so that I can't be bothered by all people from the real world. I will want to be only with the people in my simulated world. And of course, what happens is that, well, the cloud provider in which he is having the service says, oh, this guy has disconnected all I/O. I can optimize all the process to nothing. So is the guy still alive? That's a question. That's a philosophical question of the book. But there's still a handle on the process, and the process is just been optimized to a NOP. But in general, you can do things like that dynamically with programs. Just optimize away things that are not observed. Simplicity, yes. If you separate, I argue that if you factor your code in such programs and meta programs, you can tremendously simplify your code, because now the code that does not have to care about all these things. It can share your file selector or your UI with everyone else. So instead of having every program come with an entire library of window specific management, and that will only run on your existing computer, and then you can't migrate because you're tired. Oh, I linked my library against an X library, or I linked it against the macOS or the Windows or the Android or whatever, and I can't migrate my files. But I also have the liability of, when I want to analyze my program, I have to analyze an entire big library. I have imported all this library into my program, and so I've imported all the bugs from that library in my program. And if I want to change something in my program or change something in the library, now they come together. So I've made a package deal of the two. And from the point of view of either semantic analysis or security, or it's a horror. It means that you can't do what you want. You have to do more than you want, and you have to import all the bugs that you don't want. It's very bad. So if you have meta programs, they can evolve separately. You can distribute them separately. You can have different sharing policies. You can, for state, any state that exists, and you can configure them separately. And they can have separate capabilities in terms of security. So you can do a separate security analysis, and you can much simplify security analysis, much simplify any kind of semantic analysis, and have much smaller attack surface for your system. And it's, once again, not just a library, because when you have a library, you include all the semantics of the library. When you have metaprogram and program, there is a clear semantic separation. In some ways, the metaprogram can do more than a library. In some ways, it can do less. It can do more because it's bound at runtime, so it can do things at runtime that has to be fixed at compile or load time for a library. It does not have to respect the scope of your program. When you say, I want a magic number, it can do all kinds of tricks to give you a number using memorization or any kind of thing that would record state, but the state, you can have a pure program and a stateful meta program and analyze the semantics such that you know that the program is correct just because it's correct independently of the input you give it, and yet you do some nice tricks at the meta program level. So a library has to respect the scope that it's given. A meta program doesn't. A library can do arbitrary things. A library can change the semantics of your program. The meta program is not allowed to change the visible semantics of your program. unless it's a controller metaprogram and the user specifically says, oh, I want to do something. I want to side effect with the state of my program, then you do it. But a normal metaprogram that correctly implements your program is not allowed to change the semantics. And different control flow, once again, an implementation metaprogram can instrument each and every implementation instruction. It can parallelize, it can change the order of instructions. As long as abstract meaning is preserved, it can do all kinds of things. A library cannot do that. A library cannot change the control flow of the program it's running. So it can do both more and less than a library. It's a different concept. And there are many related works and opportunities, so this is the end of the talk. So what I describe is related to lots of work in formal methods such as refinement and etc. It's related to open implementation and aspect-oriented programming. It's related to many hacks that you may have heard of how people do garbage collection or migration or persistence in this or that system. It's related to a lot of work being done in virtualizing and distributing software on cloud services. And the common theme, I suppose, for my architectural proposal is that it's about programming in the large, not in the small. That is, if you want to ask me, how can I write a 10-line program that takes advantage of first-class implementation? Of course, I cannot, because it will be simpler to write a 10-line program directly at one level if you know exactly what it needs to do forever and ever. For me to give you an example, I would have to give you an example where the metaprogram has to change at runtime for the thing to be meaningful. So I would have to give you at least 2 different metaprograms and a program that can be useful with these 2 different metaprograms. So even a small example would be somewhat medium-sized. But I argued, though, that first-class implementations can help your software architecture scale. It can help you simplify your software architecture. And it is a thing where semantics matter. It's important to have either things that say, yes, I'm going to change the semantics, or things that say, no, I'm never going to change the semantics, and distinguish clearly between these controller metaprograms and these implementation metaprograms. Ones that are allowed to change the semantics, ones that are disallowed to change the semantics. And I argue also that it provides you dimensions of modularity beyond the usual splitting a program in libraries. Okay, so my take-home points were implementation goes the other way of abstract interpretation. Safe points are a key concept. First class is the opposite of magic. It's about making things visible to the users and magically done by the system. And first-class safe points are very cool. They allow things like migration and many other things. And you can then compose that implementation for fun and profit and have a new kind of modularity for your program. So can you put that in your platform? And can you then factor your software into meta levels like that? I think you can, and that you will enjoy simplification and robustness and security for your programs. And my meta story is that my contribution is not technical. That is, everything I've told you has been done in one way or another, maybe not in this form, but it has been done in one way or in another. What I'm trying to do is more ambitious. I'm trying to change the point of view about computing. I think that it's just the same old thing, but seen in a new way that makes things simpler in a different way, that make different things simpler. And if you enjoy what I told you today, you can read my blog, queenmcomputing.github.io.
How is it pronounced?
Imagine a horse whinnying, whatever. Okay, well, that's all for today. More questions? So Ed, are you going to never invite me again?
No, this is good. Matt Might has his stuff on abstracting abstract machines, right? So does this mean that you need now to have concrete implementations?
Yes, something like that. It's the same thing. Just look at the.
You just need to just dualize his paper, and I'm pretty sure you have some publications.
It's probably exactly the same thing.
No, maybe it's just a co-publication.
Yeah. Oh, okay.
So that'd be publishing it into a code journal?
A code what? Sorry.
No,
I said a code journal.
extracting it from a code journal.
Yes.
Sorry, could you repeat the name of the paper?
The abstract machines or something.
No,
But
your paper.
my paper, I don't have a
Your
paper.
thesis.
My thesis. I never published it, but it was called the Semantics of Reflective Systems.
Aborted.
Apologies for that. And maybe I should finish it now.
So I fully understand why you might have punted on this because it gets into some hairy math stuff.
Yes.
But the difficulty of these sorts of systems is the moment you want to go to infinite anything, infinite types, infinite loop executions, infinite towers and turtles.
It's also
Do you handle that,
infinite.
or do you just really punt on that?
So yes, I don't think there's anything infinite. All my towers are actually finite. It's rooted, it's grounded in the hardware. It's just that you can change what's underneath. You can add levels or remove levels, and you can add turtles. Actually, you can lift your tower and add a turtle underneath. That's the cool stuff. But I think the way I aborted was that what I was doing was way too abstract for most concrete people, and it was way more too concrete for most abstract people, you know?
Yeah.
So for Patrick, who cares about implementation? What the important thing is like abstract interpretation, things like that. And so all the theorists say, this is way too concrete, and all the practical guys, this is way too abstract and theoretical. So I didn't have my public. I think I have a larger public now, so thank you for being my public today. Another question? No? 3, 2, 1. Pizza! Thank you for coming.
3 minutes to go.
Yeah.
So this is actually probably going to be our shortest night of recent memory, unless we have lightning talk things. Just kind of a status update from me. The summer of Haskell is coming along very well. We have 37 student applications and funding now for 5 Haskell students and 2 students who are earmarked for quote-unquote Code World projects for Chris Smith. So we actually have students, some funding. So despite the fact that Google pulled the rug out from under us this year, we will at least get something done. I still have to get like the process for us to actually review all the student proposals and get that together. If anybody's interested in mentoring or what have you, feel free to email me and say hey. We'll see how, if we're going to get through the student reviews this weekend, or if I'm going to have to punt and lengthen the schedule by a week or so. Does anybody have any like quick lightning talk kind of stuff they want to do, or should we just wrap early? Well, we have the room for a little while. So.